Now we've come to the fun part. You're going to start putting electric devices together on your breadboard and giving them some actual energy to see what happens. But before we do that, you should understand a little bit more about how electricity flows through the circuit. In this course, we're going to be using lots of what we call circuit diagrams. A circuit diagram is just a visual 2D representation of how you're going to connect electrical elements together. It's not supposed to be a physical layout because how it looks on your breadboard is going to be very different, but rather a conceptual layout so that you can do some mathematical calculations to figure out exactly how much voltage and current is being applied to each of your systems. Here is an example of a circuit diagram. It has 3 different symbols all connected with lines. The symbols are standardized and represent different electrical items, and you can look up all the different symbols later. Here we've got a circle with a plus and minus sign representing a DC power supply. Then we have a triangle with a line representing a diode or an LED, and then a squiggly line representing a resistor. In this case, they are all connected one right after the other in a complete circle. A circuit has to come back to the start. It has to be complete, otherwise the electricity won't flow. Let's talk a little bit more about how electricity flows through the circuit. First, we have something called voltage. That is the difference in electrical charge between 2 different points in your circuit. You can kind of think of it as the potential electric force. It's measured in volts. In our example, before you saw that we had a DC power supply that maybe in Raspberry Pi situation would supply 5 volts. That 5 volts would flow through the entire circuit, being used up by each individual element until it hits the supply again, and then it supplies a new 5 volts to the circuit. Then you have current. Current is about the rate at which the charge is flowing throughout the circuit. That's measured in amps. And then you have the resistance. That is the opposition to how the current's going to flow through your circuit, and that's measured in ohms. You have devices called resistors, whose only job is to provide resistance, but actually every single element typically has some amount of internal resistance associated with it. In order to figure out how much voltage is being applied to each individual electronic component, you're going to want to use this incredibly useful equation called Ohm's law, which states that the voltage, or V, is equal to the current, or I, multiplied by the resistance, or R. It's important to pay attention to how much voltage and current you're supplying to each of your items because each of your items were designed to only handle so much. So if you give them too much power, they might burn out. Or if you don't give them enough power, they probably won't turn on. You can think of voltage, current, and resistance sort of like water. So let's imagine the charge, or the flow of electrons, is the water in a system of pipes. The voltage is the pressure of the water, so with how much force it's moving through those pipes. The current is the flow, or the rate at which it's moving. And then the resistance is sort of constructed by the width of the passage. Let's say you have a pipe and you fill it with some amount of water, and then it spits out at the end. Well, that water is the charge, and the voltage is how much water you put into it, and then the current is the rate at which it comes out of the spigot. Now, if you put in more water, well, that's going to increase how much is going to come out the other side. Now, what if you return to the original level of water, but you restrict the pipe? Well, it's going to produce the same amount of water, but in a much faster rate, because it's sort of like squeezing a garden hose. It's not a perfect analogy because water only flows one direction, whereas current flows in a circular pattern, but it can generally help you understand the difference between voltage and current. There's a few different ways for you to connect each of your individual pieces together. They're what we would call series connections or parallel connections. A series connection is when you just directly connect 2 electronic elements, one right after the other. Just like our diagram before, let's say we have a battery and we can connect it directly to a diode, then directly to a resistor, and then directly to another diode, and then it goes back to the battery. In this entire loop, all of these items are going to share the same current, meaning electrons are going to be moving at the same rate throughout all of these. However, the voltage is going to slowly drop as we get further away from the battery, and then it'll pick back up once we cross the battery and supply more voltage to it. So when you connect items in series, they share the same current, but not the same voltage. Now, parallel items are how you can share the same voltage, but maybe not necessarily the same current. So Here we have our diodes again, but you can see we've created a sort of branch. They're all still connected in a circle, but there is a nexus point after that first diode where the electricity is going to flow in two directions instead of one. This is going to split the current, but it's going to still provide the same amount of voltage. Don't worry, throughout this whole course, we're going to tell you exactly how to set up your instruments so that you don't burn out any of your pieces. And we'll give you a better idea as to why we're choosing each of those devices as you go along. Also, as you can see, Ohm's law is a pretty simplistic calculation. It's just multiplication or division. So you shouldn't be too intimidated by doing the math of each of your electronic devices. And we're here to help you through it.